Good afternoon, everyone. Today, the Autonomous Seminar has the great pleasure of welcoming Professor Mohamad Moosavi. Professor Moosavi received his PhD from École Polytechnique Fédérale de Lausanne in Switzerland. He is currently an assistant professor in the Department of Chemical Engineering and Applied Chemistry at the University of Toronto, where he leads the Artificial Intelligence for Chemical Sciences Lab. His research focuses on artificial intelligence, molecular simulations, and autonomous discovery methods to accelerate the design of advanced materials. His work also includes porous materials such as metal organic frameworks, covalent organic frameworks, and zeolites, with applications in energy and sustainability. So once again, welcome, Professor Musab. Thank you so much for accepting the invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Thank you for the intro and also inviting me to your seminar series. I got to know about your seminars through YouTube and I looked it up. So many prominent researchers and speakers you already have had, and it's really a delight to be part of those cohort and give us talk here. I'm an assistant professor in chemical engineering at the University of Toronto, part of the Vector Institute and Acceleration Consortium, which is having an ecosystem around AI for material discovery. My focus of research is on AI for sustainable technology development. And this is my team. I'm going to talk about their work today. And it's great to be with you today. Just to get started with where I am entering this field, I would like to look into this paper we wrote a couple of years ago. It was a perspective in 2020 on the role of machine learning for understanding and design of materials. And for me as an engineer, the way I look at it is that we usually have a problem to solve. Let's say we are interested in a separation application. We come up with a process design for that. Let's say a temperature swing adsorption or a membrane that needs to separate two gases or a reactor. And after we design our process or device, we come up with some performance indicators which basically guide us through what are the optimal setting that we need to have. And it can be as simple as some material KPIs, or it can be very complex environmental impact of the entire process. But from a material discovery perspective, our goal is to explore chemical compound space, like all porous materials, all polymers, find the one that has the right properties, synthesize them, evaluate them in this process that we had to get the KPIs, and then go back and search for the better materials. And this was 2020, and I think since then the field has progressed significantly. Almost in all aspects of this, we have demonstrated that AI can help doing things faster and better. What I see the next step for us to make progress is to make AI multi-source, multimodality, and multi-scale. What do I mean with this is that we need to have AI that can process various modality of data, not just tabular data that we use to train our machine learning models with. Like our AI models should be native with crystallographic data. It should be able to look into a spectroscopy. It should be able to look into all aspects of data, but also from different sources. Computational chemistry is the field I have worked a lot on, but there is a lot of information in the literature. Experimental data constantly generated with automated labs are another important sources of data. So we need to be able to have data from different sources. And then ultimately, the goal of all these to deliver some impact to the world is to connect different skills. While we might be working, I don't know, in synthesis lab or in computational chemistry, our ultimate goal is delivering some technology for making some good impact to the world. So we are now moving toward AI systems that can work across these modalities, sources, and scales. And probably the thing that comes to mind whenever someone talks about AI these days is about large language models, because they can consume all sorts of data modalities and they work across domains. So we, as a one starting point, we thought, let's see if we can evaluate these LLM models for doing scientific research. So we teamed up with a bunch of other colleagues in different universities and institutions to evaluate large language models in scientific research. And our motivation was very simple, because there has been a lot of interesting and good benchmarks for LLM for other domains. We wanted to make something similar for science. In particular, our distinction here is that we think science is not like a quiz that you just have a bunch of questions and answers that are just valid in isolation, but you need to link them into scientific projects to make them meaningful. Because what happened in the benchmark development community is that people came up with very hard questions and sometimes irrelevant questions. These are not entirely meaningful for evaluating the performance of these language models in scientific domain. So that's why we end up building our scientific discovery evaluation like this. We have different domains, we have different projects and scenarios, and for these scenarios, we come up with a set of questions that are relevant for scientific discovery. What we found is that while the performance of these LLMs are really high with, answering questions in chemical engineering undergrad curriculum or answering questions in material science, they're not entirely useful at the moment for doing autonomous research on their own. If you look at the evaluation metrics that we have, the benchmark is not saturated. So the LLM, the large language models, cannot really solve all the problems that we have in our benchmark. And more importantly, by adding reasoning efforts and also increasing the model size, that's the two direction that the community is pushing forward. We see that the performance is saturating and you don't really get better than a certain threshold. So what we observe here is that we need to think about what are the limitations of these models and how can we make them better. One aspect of it is that, what we have at the moment is very powerful models, but they have large capabilities, but then to make them useful for scientific research, we need to build an environment around it so that these LLMs or other models, they become very useful and impactful. And that's what I call a scientific harness, that is building a knowledge base, data and language and tool around these large language models to enable scientific discovery. And now I would like to focus on the field that I'm doing research. This is the field of metal organic frameworks. I have seen you have many speakers active in this area, so I will not spend too much time explaining what are MOFs. Basically, these metal nodes, organic linkers assembled on 3D networks, making these porous structures that has a high surface area. And this high surface area allows you to do all sorts of interesting application that you require basically surface phenomena like gas absorption, photocatalysis or catalysis, or sensing, drug delivery, all sorts of things that you can imagine that you need high surface area with per gram of material. And there has been many of these materials synthesized. There are many more predicted in computers, so it's an interesting field to use this area to see if we can build a scientific harness around it. So the first aspect is to see where are data for MOFs. So we did a text mining study that we looked into about 10,000 MOF papers. What we observed is that there are different domains that we can categorize these papers into. People who look into MOFs for photoluminescence, people who look into MOFs for carbon capture, and so on and so forth. Interesting thing is that there are a lot of common characterization techniques that people and properties that people report among these fields. Like, for example, water stability or thermal stability are the things that people in these carbon capture and photoluminescence pay attention to. It's not just one area or one domain that people need to have a thermal stable MOF. And that's an interesting observation because often the way we develop machine learning is based on domains that we silo some data, we collect data from our field and we train a machine learning model. What we want to do is to enable AI models that can learn across domains, not just from the data in my field. So that's why we think it's important to take the first step, unifying the data across these fields, instead of just saying, I only care about carbon capture, and I collect data for carbon capture papers. So, and one aspect is that we, in addition to data like computational data or crystal structures, we would like to do a collection of experts' insight and also experimental data from these papers. So ultimately, what we want to build is something like this graph, that every material is nicely connected to the potential applications. We know how to synthesize the material. We know the computational properties of these experimental ones, and so on and so forth. So to build such a data set or such a knowledge graph, that here I'm giving you an example, like a MOF as a synthesis procedure, a bunch of computational properties and experimental properties reported for it, and applications that this material was considered. We need to unify the data. But we faced one simple challenge, and that is the fact that in different domains and different computational and experimental modality of data, people report materials with different names. There is no standard way of reporting data and also naming materials. For example, if you read papers, people talk about copper BTC as HCAST1. That's the convention that people use in the field of metal organic frameworks to name their material after the name of their university. HCAST is for Hong Kong University. This is Hong Kong University 1 framework. And then if you look at the computational databases, like the one that I work with, I actually don't use HCAST1. I use this CSD, Cambridge Structural Database reference code, BODPAN, which is a meaningless reference, but it's a 6-letter referring to this particular compound. So if you want to unify things together, we need to first resolve this. So that's the work that Amro and Thomas, my PhD student and master student, did. They developed a multi-agent system that first starts from a material in CSD. It takes the material and goes to the paper, finds what are the names that are used to refer to this particular material, extract all those, put it in the knowledge graph, and then start extracting properties that are reported for this, like these experimental values that are measured in the paper, the application that this material was considered for, like the optical devices, how to synthesize the material. We extract these as well. And then when we have all these, we put it back and build this huge knowledge graph. And now you can actually chat with your data. You ask, summarize all the information you have for HCAST1, and it reports what kind of things are reported in our knowledge graph for this particular material. So this is a nice way of how you can unify data and the literature and computational resources. This work got published last year in November in JAX. And something I like to mention here is that now we also see the impact from our field, like computational chemistry, AI for materials, in the field like computer science. Basically, this is My students got the award for ChatGPT Future class of 2026. These are like 26 teams in the world across all areas of science and engineering that they demonstrated some useful practical application of ChatGPT in different domains, and I am really proud that these students got the award. But then what can you do when you have such a data set? You can actually make a simple chat system that when you ask a question about a particular material, instead of large language model answering you, you can query some information from the database that you have and then answer this based on the information that is available. You may be wondering, is it better than simply asking this question from ChatGPT? And at the time, we tried this. So if you, for example, ask this ULMOF5 water stable from ChatGPT, the very smart thing that ChatGPT is doing is that it guesses that people use name of university to name their MOF. So it says ULMOF5 is University of Louisiana Metal Organic Framework, and it's not water stable because it is a zinc-based. It's similar to many zinc-based MOF. If you run it again, it also says ULMOF5 is a variant of MOF5 this time. It doesn't say University of Louisiana, and it's constructed from zinc atom. But interestingly, while this is very smart from ChatGPT, it's all hallucinated results. In fact, ULMOF5 is a lithium-based ultralight MOF5 framework, so it's not University of Louisiana or MOF5, and it's not zinc-based, it's lithium-based. So this is just pure hallucination, which is really hard to filter when you work with large language models. In contrast, if you use the system that I just shown, you can actually get very good answer. If you ask the same question, what you get as an answer is that first you get a query of what is ULMOF5, and then it gives you this answer. It says ULMOF5 is not water stable as indicated by its property of being unstable in water. This is justified by text that states this is soluble in water and methanol. And if you go, and it gives you also a citation. If you go to that paper that reports this, the interesting thing is that the sentence that says ULMOF5 is soluble in water is not talking about ULMOF5. It talks about compound 1 and 1A. That's how people usually report in papers. They define the MOF, they give it a name, and then use a co-reference along the paper talking about different properties. So that points out the importance of this name co-reference resolution that we did at first to make sure that everything is trackable to the original data that is reporting a particular property for a material. Now, we can do some cool analysis with the data that we have. For example, expert recommendations. Everyone who writes, a paper about synthesizing a material that is good for carbon capture, they usually suggest why they think this is a good material for carbon capture. There's a competition to find the best material for a certain application. So what we did was looking into all the materials that we have in our database. This is the entire material database. Each dot is showing one structure. Here it's a lower dimensional representation of this space using cheminformatic descriptors. But materials with, for example, low pore volume are clustered here. The materials with high pore volumes are here. And we can now see how people recommend materials for a particular application. One application in our case is methane storage. You see that the blue ones are mostly on this side. The other one is carbon capture. It's basically everywhere on the chemical space. Now we can look at the distribution of the properties that we have for these two applications. For methane storage, the recommendations from experts is actually very good. So this blue one shows the distribution of methane uptake at a certain pressure compared to the full database. And in fact, the recommendation from experts is very good in this case. In contrast to carbon capture, where the recommendation from experts, the blue, is not that better than just a random sampling from the entire database. The reason that we think this is happening is that first, it feels like carbon capture is more complicated than methane storage. The performance indicators are not easy to define. Usually you need to evaluate a material in a process level to understand its performance. So there are various reasons that one might claim the material being good for carbon capture versus the others. And also, probably the field of carbon capture was more hot over the past decade, so that made people claiming victory for various reasons that are not entirely practical. So this is some interesting data analysis that we can do, but more than that, we can convert these expert recommendations to something useful, because now we have connection to materials and their similarity in this chemical search space. What we can do is to say, okay, if an expert says this is a good material, we can look what are similar materials to this specific material and say how they would perform for this application. And you can see the green is following very closely the blue, which is showing that now we can convert experts' recommendation to something useful, because traditionally this is not easy to make it actionable. Now we can do it. Other interesting thing we can do now is to distinguish between the language of materials and natural language. If you ask ChatGPT or other language models, recommend a MOF similar to HCAST1, what it does is that it finds material that are similar in terms of the language representation of HCAST1. While in fact, what we care about is not the language similarity or natural language similarity, but actually material similarity. So if you look at the suggestions from ChatGPT versus our model, when you look into the chemical compound space, you see that if HCAST1 is here, the one that was recommended from our system is actually very similar to it, while the one from ChatGPT is not entirely similar. So this is another important aspect to think about when you think about scientific hardness. The data matters, but also the language matters. We don't necessarily can use natural language for processing material data. We need to develop material native language. And one study that we have recently done on X-ray diffraction data, for example, is the one I'm going to talk about later during my talk. Other useful thing we can do when we have unified such data set is to have property predictions from machine learning from experimental data and computational data. For example, if you want to design materials for carbon capture, for CO2 uptake, usually we can predict the CO2 uptake by computational chemistry. We can run GCMC simulation and calculate the uptake. The water stability, on the other hand, is not something easy to compute. So what we can do instead is to collect data from the literature. That's part of the MOF community, that we collected all this data from literature. People report water stability, and then we can use those labels to train a machine learning model. This shows that, in fact, we can get a good prediction. Predicting water stability is possible with these models, and it reaches a good accuracy. So we can have multi-property machine learning models that are trained on different aspects of the data, different sources of data. Like any other data set, it's also important to have an ecosystem that you can expand the data set, not just having a snapshot, but actually being able to have an ecosystem that can evolve over time. The nice thing about the knowledge graph is that you can resolve all the connections between data and simply expand it by adding new data points to it. So let's say we want to find out what are the ways to synthesize this material HCAST1. The one that we had in our MOF community database was this CST sources, the one that was shown here. But if we go and do a literature search, there are many more papers that talk about HCAST1. They report a way to synthesize HCAST1 in their paper, but they don't necessarily deposit a crystal structure in CSD that we included directly in our MOF community. So then you can see that we can collect all sorts of data, about 50 recipes here for synthesizing HCAST1 and directly linking it back to the specific material that we are interested in. So now I would like to talk about how we are thinking about expanding this database on the computational side of things. So here, this was about expanding things from extracting more data from the literature, but how about computational chemistry side? I initially shown you this schema here that each MOF has a node that is, each MOF is connected to a node that is computational properties. But under the hood, what is happening here is that each MOF is represented by a crystal structure from core MOF database or QMOF database. These are the very foundation of basically most machine learning models that are trained for MOFs in the past 10 years. Core MOF database was developed by Greg Chung in Korea and also Gubin Zhao. And also QMOF is developed by Andrew Rosen. These are phenomenal work that we build a lot on top of them. So we basically use these databases as the foundation and core of our MOF community work. But if we want to now expand it, what we can do is to say, okay, a MOF has a this is the previous schema, but now a MOF has a computation-ready CIF, crystal structure. We want to do DFT optimization of the material and then calculate the set of properties that we are interested in. And now, since we have all this schema and this knowledge graph ecosystem, we can put all this data back to the database. So the goal here is to revamp the core of MOF community by doing DFT optimization of structures and computing a sort of set of properties, in particular the adsorption properties that we are interested in. How do we do calculation? Probably they have seen this emergence of universal machine learning potentials for material modeling. These are neural networks that take crystal structure as input and predict energy and forces, basically. Very similar, or not basically identical to a force field, but instead of rigid formulation of force field, the functionals are not rigid. They are just basically flexible neural networks that can learn quantum mechanical level of interaction between atoms. So what we wanted to do was to use this for building and improving our database. So first we did a benchmarking of these machine learning potentials, or universal machine learning interatomic potential, or UMLIP in short. To design this benchmark, Henrik and Zhu worked together to systematically evaluate structures from QMOF, mosaic database, IZ8, these are zeolites and COFs, using about 22 machine learning potentials on various tasks. So we didn't want to just say, if energies are good, we are good. No, we wanted to see if we do DFT optimization, if we do molecular dynamics, if we do bulk modulus calculation, how well these machine learning potentials work. And the interesting thing we observed was that, in fact, they work much better than state-of-the-art models, including force fields that we have been using for a long time. But the interesting thing we observe is that also there are a bunch of these models available. Like there is a zoo. You can see all these names like Equivariant 2, 7net, Grace, ESEN, MACE, MatterSim. But the very important observation for us was that, okay, this field is evolving very fast. So this was the first machine learning, universal machine learning potential that was introduced in 2024. Almost after a year and a half, we reduced the error of this model a lot. and we got even better than a fine-tuned model that was made particularly for the material that we are interested in. So it shows rapid progress, but also what it shows is that the data is actually the main bottleneck at the moment, not the models. So these models are doing different architectural design from neural network perspective, but if you look at carefully about the performance of these models, this MatterSim is an outlier, but look at these. As soon as you have a new database like OMAT, this is an open material data set, the performance of all models actually got better. It's simply because all models have a very good learning capacity. What matters is the input data. So more data is more fundamentally important than making your models better in terms of neural network. So that's an important observation, but also from practical observation, what we see is that these models are actually becoming useful and even better than the one that we used to use for a long time. And in particular, if you are evaluating them for optimization, crystal structure optimization, this is the performance of all sorts of models compared to DFT. So we take a crystal structure, we do DFT optimization, and we take it as a reference, but then we take all sorts of machine learning potentials and do optimization, and we compare the delta volume in the final crystal. You can see that the classical force fields like this is not great. The fine-tuned machine learning potential is doing okay and actually pretty good. But some of these machine learning potentials, like ESEN, is getting very accurate. And this also shows in how many steps of optimization you converge to the final solution. So you see that these machine learning potentials are actually very powerful now for doing optimization of crystal structure. But one thing we were not 100% satisfied was that at the end, it's a bet you make. Like, you are doing machine learning potential, you are not sure if this final structure that you end up, is it valid fit DFT, or it might be also still some error from the machine learning potential. So that's the approach I think is important, that we always do the final step at DFT validation to get to make sure things are converging to the right solution. And also, to make it even more iterative, Zhu developed this workflow that she runs DFT steps after series of machine learning potential steps, collect the data, fine-tune the machine learning potential, and then repeat this and do this iteration multiple times to do the final obtain the final optimized structure. So this iterative fine-tuning of machine learning potential plus DFT validation gives us very good results. And in fact, we get results better than DFT alone. So here, since this is a relatively crowded figure, I would like you to focus on this figure on the bottom left. We are showing number of DFT steps to end up with the final solution. If you just do DFT, but let's say, and your budget is 200 steps, you converge to for about 60% of structures to the final solution. But if you combine this with machine learning potentials, so let's go for the one that beats out fine-tuning, you get to about, 92%. And if you go a little bit more with fine-tuning, you can push it to about 97, 98% of the crystal structures. So it's very efficient now in terms of getting your results. So that's an important improvement. But it's not just more fast or more efficient, it's actually better, because if you look at the energetics of the crystal structure that you have at the end of this and at the end of the optimization, you see that in almost all cases, 91% of cases, you end up with a crystal structure that has a lower energy. So each dot is showing one crystal structure, that is going through this iterative fine-tuning and DFT optimization steps. And then we monitor and compare the energy of the structure compared to one structure that is fully DFT optimized. If the energy is lower, we found a better optimum. And you can see that in almost all cases, we got it better. And remarkably, with only 15 steps of DFT, you get 83% of materials finding a better solution. So based on these observations, with this benchmarking we did, we decided to limit our DFT steps to 15 to save budget, because if you want to let the DFT to complete the work, it goes on average or on median like 53 steps. But that 53 steps doesn't add much. For 83% of materials, you already get it right with 15 steps already. So that's what Zhu implemented as this MOF community core, that is DFT optimization of structures in core MOF database, and then further computing all sorts of absorption properties. So this is MOF community core study. It has about 7,200 DFT optimized structure, 5,000 partial charge calculation, like gas absorption for all sorts of gases, and then also computed mechanical and thermal properties. So these are just data that we collected and added to the MOF community as an environment for storing computational and experimental data for MOFs. All right, so this is just the last part of my talk. I talked a lot about building an environment for storing and manipulating MOF data. I just want to show an example of how interesting and useful these things can become. By looking into this question, we always ask that we want to discover a material for an application. But what we can see also is that there are a lot of materials made every day in the labs around the world that don't end up being used for any application. So we want to ask the other way, can we find a potential application for a newly made material? Because in our previous research, what we found is that there are a lot of interesting materials that are overlooked because, for example, someone synthesized this material for photocatalysis, but then 7 years later, someone may find the same material that is being very good for carbon capture. And this is not the only example in the literature. There are many more. And in particular, academia is very well equipped with this because usually we are limited to the type of characterization we can do. We may be interested for one application, but we have a friend who works, I don't know, on carbon capture. We can send a sample to them if we know this material is potentially useful for the other application. To make a useful model that can recommend application, we needed to make a model that only takes data that is available upon synthesis of material, not necessarily the clean crystal structure or fancy machine learning methods, simply data that is available upon synthesis. In our field, this is basically the precursors that are used for synthesizing the material and the PXRD pattern. The PXRD pattern just proves that the material is crystalline and it is formed. As soon as you have these two, you can say the MOF is formed. So Sertaj worked on this project to connect these two modality of data to properties and recommend applications. What he did was building a fancy machine learning model that takes crystal structure as one input, these two as another input, learn an embedding that basically infuses information from crystal structure into that learn embedding. This is the pre-training phase. But after you pre-train the model and you have all the information about these three modalities, you just you get rid of this top part. You keep only the bottom part and make predictions. The results were promising. So if you look at the results, if you only take the crystal structure based model, for example, it's the blue one. This is the blue one here. The model that we have is PXRD and precursor. This is the green one. And across different properties, band gap, methane uptake, surface area prediction, xenon uptake, density, we get very good performance. And interestingly, these two modalities, the one of PXRD and precursors, they capture different aspects that matter for our application. So PXRD is very good with the spacing of atoms in 3D space. So it's basically capturing the pore geometry and pore volume, pore geometry related properties. On the other hand, precursors capture the chemistry and reliant properties. So if you remove one, for example, PXRD only, it fails very badly predicting band gap because it's highly chemistry dependent. On the other hand, if you remove precursors, you see that band gap is still okay, but the geometric property dependent properties are really poor now. So this is showing us that the combination of these two can be very powerful. And in fact, now we can connect synthesis to application. So here is a map showing the embedding space or the learned space of these models. Each dot here shows one material, and different colors shows different applications that we have in our study. So if a material is suggested to be good for methane storage, it's this color, and so on and so forth. What we observe is that for these storage applications, we need to have high pore volume, and these are the area of suggested materials. The interesting thing is if you look at, or if you color code this map with, for example, crystal density or pore diameter, you see that materials with very high density are all clustered here, low density are here. These are the ones that are very promising for methane storage, hydrogen storage, xenon storage. So essentially the model learned something that was not the input of the model itself. So we inputted this model, the one that is shown here, just peaks, RD, and precursors, but it organized these information in a meaningful way that has information about, for example, crystal density that is important for different applications. So now we can use this model to suggest different application for a newly made material simply by inputting the peaks, RD, and precursors of the material. All right, so that was my talk. I talked about AI for material. I talked about LLM benchmark and how this gave us some indication of the failure modes of these frontier models. And I talked about how to build an environment for making these models useful. One about MOF community, which unifies data across different modality and sources. The XRD, the one I talked about, was briefly touching about representation learning, how to use representations, for example, for PXRD. For tools, it's coming. I didn't discuss it in this presentation, but hopefully once we publish a few work, we can talk about those as well. Thanks so much for your attention, and I'm happy to answer your questions.